Alright, so we're finally going to get to probability. We've been alluding to this idea of likelihood things are going to happen, the chance things are going to happen in Chapter 6 and in 7.1, right? And so now we're going to finally get to probability in this section. So this 7.2 is sort of the beginning, the basics of probability that we're going to build off of for the rest of Chapter 7. Now, we are still going to use counting techniques. We're actually going to use them twofold, which I was trying to foreshadow in 7.1. We're going to have to count how many's in the set we're universal set, right? The set we're under consideration, and we have to count the event we're interested in. Alright, so we will still have to do counting. The basics of probability, there are two types of probability we're looking at. There's what's called relative frequency probability, and that's the one we're going to get to in this video. Also known as estimated probability, and I'll explain why it's called estimated probability when we get into that. And then theoretical probability. We'll get into theoretical probability more in the next section, in the next video, this section. This is where the counting techniques come into play when we do the theoretical probability, the Chapter 6 counting techniques. But that's the next video. This video, we're going to go over relative frequency probability. Right, so just so that we're clear and understand what probability is, right? You should know what probability is, but if you don't, when we use the term probability, what we mean is the chance something's going to happen, right, based on frequency numbers or based on theory, what we understand about the experiment, whatever we understand about what's going on. It's the likelihood an event's going to occur based on the numbers, based on the theory, right, based on what we're talking about. All right, so again, there's two ways. There's the relative frequency probability, and that's based solely on past observations, collecting data, getting statistical information, and basing a probability off of those numbers. Or the theoretical cases, which again we'll use our counting techniques, our permutations, our combination, and this is based on the likelihood of an event happening using what we understand about the event, right? Like flipping a coin. I understand when I flip a coin, there are two outcomes. One of the outcomes is heads, and one of the outcomes is tails. And so whenever I flip a coin, I have a 1 in 2 chance of getting heads, 0.5 probability, or 50% chance, or a 1 in 2 chance, right, one outcome out of 2, to get tails. Right? That's the theoretical probability, based on what I understand about the experiment. Right? Which, like I said, we'll get more into theory next time. This time we are going to stick mostly with this particular video. We're going to do mostly relative frequency probability. All right, expressing probability. All right, probability of an event. So don't get this confused with permutation. This would be probability of whatever event we're interested in, knowing the likelihood of, right? The probability of flipping tails, or the probability of rolling an even number, probability of rolling a sum of 10. Probabilities are always written between fractions or decimals, written between 0 and 1. All right, 1 is the maximum probability, 0 is the minimum probability, and then everything in between. Right? There aren't any probability numbers between 0 and 1. So whenever you write a probability, all right, probability of my event, that number that you write down should be a decimal or a fraction that's bigger than 0, so positive. If you ever get a negative probability, you've done something wrong. And it should never go over 1. Right? If you get a probability bigger than 1, you've done something wrong. It's not possible. You cannot get a probability bigger than 1. 1 is my maximum. Right, what 1 stands for, so the probability of getting 1 out. All right, 1 is the maximum probability, and that maximum probability means when I have a probability of 1, I'm guaranteed that event will occur. Right? You're guaranteed it will happen. Probability event will happen is 1. The way we typically interpret probabilities is percents, right? You can write a decimal as a fraction or a percent. Right? Well, when we talk about the probability is 1, when we talk about it, we do typically talk about it as converting from the 1 to the percent. So a probability that something is going to happen is a 100% chance that it's going to happen. It's guaranteed 100%, and you can't go over 100%. 100% is a guarantee. You can't go over the guarantee, right? This is the maximum probability. Right? It's going to happen. Right? The probability of an impossible event, right? An event that cannot happen. right, would be the 0, right? Probability of 0 means that event cannot occur. It's impossible. 0% chance, right? The probability is 0. The percent chance is 0, right? 0 means there's no way it's going to occur. Right? And then everything in between. Right? Typically, right, so flipping a coin, like I said earlier, was an example where you have a 50% chance of getting heads, right? You have a 1 out of 2, right? There are 2 outcomes possible, one of them's heads. So you have a 1 out of 2 chances, 1/2, 0.5, or we say a 50% chance of flipping tails, or 50% chance of flipping heads. And so that's why a lot of times when we say it's 50-50, it's a coin toss, it's a toss-up. All right? Anything bigger than 1/2 or bigger than that 50% chance, we consider likely. Now, the bigger it is, the closer to 100%, the more likely it is. Right? So again, if it's 60%, that's likely. If it's 70%, that's more likely. If it's 80%, it's even more likely to happen. Right? But if it's above 50, 50 is the flip a coin, right? 50% chance, it's considered a likely event. If it's less than 50, less than that half, that middle probability, right? 50 is a toss-up, right? It can go either way. If it's less than 50% chance, we consider that unlikely, all right? So unlikely events would be something like 30%, 20%, 10%. The closer to 0 it gets, the less likely it's going to happen, right? 30% chance is not very likely, but a 20% chance is less likely than that, all right? And a 15% chance and so on. And so usually we use sort of a scale. Right? All probabilities got to land between 0, right? That's a 0% chance. The halfway point would be 0.5, 50% chance. 1 would be the 100% chance. And then so these would be the unlikely, anything between 0 and 50. And these would be the likely, right? Anything from 50% to 100%. So again, something over here would be 0.1 would be unlikely. 0.4 would also be unlikely. Now, 0.4 is slightly better, or still a little more than slightly better, but 0.4 is still better than 0.1, right? But it's still on the unlikely side, right? Same thing kind of idea over here. If I've got 60%, we still consider that likely, but if I'm at 90%, I'm more likely, right? I'm getting closer and closer to that 100%. And so all of your probabilities have to land between 0 and 100. Anything bigger than the half is considered likely. Anything less than a half is considered unlikely. And again, higher you go, the more likely you are. Right. First type of probability is the easiest type, right? The relative frequency probability. And this is based on information that we've collected, data that we've collected through experimentation, or frequency tables, how often or how many people in a survey and things like that. Typically, these are your tables. Relative frequency probabilities are based on frequency tables, how often the tally of something happens. This is why it's also called an estimated probability. It's based solely on the numbers, right? Which estimated, it just means it's an educated guess based on our numerics, based on our numbers, all right? It's usually still a pretty good guess, all right, but it is imperfect. It's not perfect. It is considered an approximate probability of the event by making observations. The more observations you make, the better this probability gets. But it's based on what will happen given data, given statistical data, all right, or a frequency table. I only use this if the problem states it, or if it's a table type, it's a relative frequency probability. It's a fairly simple, right? This is a lot easier than the theoretical probability. We'll get to theoretical probabilities in the next set. The relative frequency probability or estimated probability of an event is pretty straightforward. All right, so this represents the probability of my event, which it's a fraction, right? That should come out between 1 and 0, where n is the total number of observations or experiments that we've done. Right? I've rolled my dice 1,000 times. I've observed or I've surveyed 100 students at Illinois State University. Right? And I'm basing my probability on that outcome. All right? So n would be the total. How many in my experiment, how many in my observation? And then the probability up top is the frequency the number of times my event occurred in my total, right? When I flip a coin 1,000 times, I figure out, well, how many times did I get heads? Right? I tally that up and I use that as my frequency. When I take a survey, how many times in my survey did the students in my survey answer in this particular event? All right? Did 5 of them answer this way, 10 of them, 100 of them? How many of them answered in a certain way? All right? That would be the frequency. How often did they do something in my total? And then you just divide, right? You take your number of outcomes in my event. So what it is, it's the number of event outcomes divided by the total outcomes. Right? The number in my universal sum. So how many ways did this happen out of my total? All right, so the first couple examples are based on observations that we've made. Alright, so the first example is a hospital recorded out of the last year. So they're making an observation out of 205 births last year. They tallied 105 of those 205 were born boys, and 100 of them were girls. Based just solely on nothing but the numbers, right? The tallies, the observations, no biology, no other factors are taken into consideration. Just the numbers, the frequency of girls, the frequency of boys. What's the estimated probability, what's the educated guess that the next baby will be a girl? Well, it would be the number of girls divided by my total. Alright, well, out of 205 observations, 205 births in the last year, we observed that 100 of those were girls. Alright, so you take 100, the event, girls, divided by the total, all births, and we get our relative frequency probability, and then we'll write it as a decimal. Right, so there's our fraction written as a decimal, 0.4878. Right, so the probability, and I rounded 4 decimal places, is 0.4878. Or if we did it as a percent, 48.788% chance. Typically, we will ask you, though, to give it as a decimal. So on the quiz, most of the time, now you do have to pay attention. Sometimes we'll ask for percent. Sometimes we'll ask for the decimal, so you should be able to convert between the two. But a lot of times when we say probability, it's asking for it as the decimal. All right, so the 0.4878. But if we say what's the percent, right, we can convert that to a percent by multiplying by 100, right? Move the decimal place over twice. Next example. Right, you roll a pair, so this one's an experiment. So the last one was observations. We based our probability on observations. This example is going to be based on an experiment. All right, I take a fair pair of dice, 6-sided dice, and I roll them 200. So again, we're physically rolling them 200 times, and we're tallying, we're observing on our experiment. We're figuring out how many times out of my 200 do my events I'm interested in occur. Alright, so we were looking at the sum of 6. Well, out of the 200 tosses, 29 times that occurred, and a sum of 2, 14 times that occurred. Right, based solely on my experimental numbers, right, therefore it's an observation, so it's an estimated or relative frequency probability. We'll actually do this exact same example theoretically later on, and see what the difference is between the two. Alright, so based on my observations, and I predict what's the probability that my sum, if I roll it again, my next roll will come out a sum of 2. Well, it's the number of ways I got a sum of 2, the frequency of getting a sum of 2 out of my total. Well, out of my 200 rolls, my sum of 2 occurred 14 times. So 14 out of 200, which actually I think is exactly 0.07. 7% chance. Alright, so the probability is 0.07 that the next roll will come out a sum of 2, or a 7% chance. Alright, based on my same experiments, find the estimated probability that the next roll will be a sum of 6. So based on my numbers from my experiment, sum of 6, well, out of 200 rolls, a sum of 6 occurred 29 times. So 29 out of 200 which is 0.145, or again, 14.5% chance. Alright, so the probability based on my observations of getting a sum of 6 is 0.145, or 14.5% chance. Alright, so those were based on data that we've collected through either experimentation or observations. The last type is given in a table. So if we're given a relative frequency table, which means we've collected data about something and we've put it in a table format, and we're going to base our probabilities just on the table. We're not going to take anything else into consideration, just the numbers from the table. All right, the frequency my event occurred using my table out of the total. All right, so the table that we're going to look at in this example is we've taken 1,000 applicants last year, and we've put them into the categories of ACT, and we've grouped them based on their ACT score. Right, so the first group was getting an ACT score of 17 to 21, and then everything in between, the 32 to 36, and then how many in our 1,000 landed in each of those groups. And then the other thing we tallied was whether they were accepted or not accepted. All right, so those are how we put them in our table. All right, so those are what we're observing. So the first question is, find the probability a student was not accepted. All right, so probability based solely on my numbers, nothing else, just based on my numbers in my table, that they were not accepted. It would be the number that were not out of my total. So out of 1,000 applicants, how many were not accepted? Well, 400. So there were 400 people not accepted out of 1,000, which comes out to be 0.4 or 40%. 40% of the applicants were not accepted. That probability is 0.4. Right? 0.4 probability. Find the probability that a student had an ACT score of 27 or greater and was not accepted. Alright, so we're looking at an and statement. So I want to find the probability they had a 27 or greater, which means they had an ACT score 27 to 36. So they had an ACT score of 27 to 36, and they were not accepted. Well, it's the number in that group in my event. I just don't feel like writing it out again in my total. Alright, so the event that you had a score of 27 to 36 on your ACT and were still not accepted. Alright, so I'm looking at two things. So I'm looking at the not accepted, and I'm looking at the 27 to 36. And so those two overlap, and I probably yellow. Alright, they overlap. Here, the 30 and the 5, right? That's the overlap. 30 students were not accepted when they had a score of 27 to 31. 5 students were not accepted when they had a score between 32 and 36. And so a total of 35 students out of my 1,000 were both not accepted and had an ACT score of 27 to 36. And so 35 was my frequency of that event happening out of my total 1,000. So the probability is 0.035, or if we write it as a percent, 3.5%. So not a very big chance, right? If you had an ACT score of 27 or greater, there was only a 3.5% chance you were not accepted. If you had both those things. Sorry, I said that wrong. If you had ACT score of 27 or higher and you were not accepted, the probability of that happening was 3.5%. Alright, the next example, I believe I just changed a little bit. I changed one little word, but that one little word makes a big difference. Find the probability that a student had an ACT score of 27 or greater, or the student was not accepted. Alright, so the difference here, and it makes a big difference, is I'm going from and to or. It changes the number of students in my event, right? The or is the set that's all inclusive. They can have an ACT score of 27 or greater, or they can be part of the group that's not accepted, and there's some where there's overlap, and I have to be careful not to count those overlaps. Alright, so probability, they had an ACT score of 27 to 36, or they were not accepted. Alright, number in my events. I just don't feel like writing it out again, so I'm just going to write number in my events over my total. Alright, so out of 1,000 students, how many were in one of those two groups? Alright, we're in the ACT of 27 to 36, or not accepted. And the biggest thing is don't count anybody twice. So I'm actually going to write my work down here. I'm going to figure this out down here. Right, number in my events. Right, I have to figure out, well, how many had a 27 to 36 plus the number that were not accepted minus the number that were both, right, who got counted twice. There's actually two ways you could do this one. Alright, so I'm going to erase this. What I'm looking at is, again, all of those that were not accepted and all of those that had a ACT score of 27 to 36. And so 27 to 36, there were 250 that had an ACT score of 27 to 36. There were 400 students that were not accepted. And then I have to be careful. These 35 were counted twice. I don't want to count these 35 twice. And so I'm going to take my 250 plus my 400 and subtract the 35 that were counted in both of those groups. Alright, so those are going to go down here into my formula, right? My union formula. So 250 students had an ACT score of 27 to 36. 400 of them were not accepted. And 35 people were counted twice, right? Because I counted them in both groups. Comes out to 615. Alright, so there are 615 students who were in either or group, right? They either had a score of 27 to 36 or they were not accepted. And so out of the 615 divided by my 1,000 comes out to be 0.615 or 61.5% chance they're in either or of those groups. Alright, the biggest thing about this is, again, make sure you don't count anybody. There is an alternative to use. I encourage you to use the formula to figure out the event so that you are careful about not counting people twice. But you could have figured this out without doing that. What you could have done is just strictly add up the people that we're looking for. Right? So we want all of those who are not accepted and all of those who had an ACT score of 27 to 36. And an alternative could have been, I could have added all of those individual numbers up. If you add each one of those numbers up, where I only count the 30 and the 5 once, that should come out to 615. Or we throw away the people we don't want. We don't want these two groups of people where they were accepted and they had scores less than 27. And so you could take your 150 and your 235, subtract them away from 1,000. That should also give you 615. So there's multiple ways to do this. You sort of, as you're practicing and working through these problems, figure out the one that makes the most logical sense to you, the one that you're going to do correctly, right? The one that makes the most sense to you, that you're less likely to make an error with. Alright, so again, make sure you do practice these. Alright, I believe this is the last one. Find the probability of the student with ACT score, can't spit it out now, between 22 and 36 or 26 was accepted. So this is an and statement. Now it's worded a little different than the first one. The first one was obviously an and because it used the word and. Right? But this is sort of a similar type of statement. They have a score between 22 and 26 and they were accepted. Alright, so they're between that and accepted. Alright, so we're looking for the probability they had a score between 22 to 26 and they were accepted. Alright, so it's the overlap between that group and the accepted. All right, so out of 1,000 people, how many land in that and statement? All right, well, this one's actually a little easier because I'm just looking here and accepted. And so the overlap between being accepted and getting an ACT score of 22 to 26 is 235. 0.325 or 23.5% chance. Alright, so that was relative frequency probabilities. Relative frequency probabilities, again, based on tables, a collection of information, or experimentation, which are typically the easier ones because it's easy to read a table for the most part. Really, only where you have to be careful is when you're dealing with the or statement. And when we're making observations, it's pretty straightforward. I got this many results out of my total, this many outcomes in my event out of my total. Alright, and so relative frequency probabilities tend to be one of the easier cases. In the next video, we'll start the theoretical probability, which will contain more of our counting techniques that we had in Chapter 6. So we'll pick that up in the next video.